Okay, Chapter 2, Large Language Models. This chapter is designed as a quick and minimal introduction to this subject, and it should not be considered a comprehensive treatment on the subjects of natural language processing or language modeling. In terms of prerequisites, I will not assume any a priori background on natural language processing or language modeling, although I will assume some familiarity with basic deep learning concepts, such as familiarity with backpropagation and the use of, let's say, the Adam optimizer. Natural language processing, abbreviated as NLP, is concerned with computationally processing natural human languages. The goal is to design and/or train systems that can understand, process information written in documents, written in text. To clarify the terminology natural language or ordinary language is any language that has evolved naturally in humans through the use and repetition without any conscious planning or premeditation. Examples of natural language would include something like English or the language Korean. Natural languages are distinguished from formal and constructed languages such as C and Python, which are programming languages, and Logjban and Esperanto, which are designed as human languages. The field of NLP was once a field that relied on insights into linguistics, but modern NLP is now dominated by data-driven, deep learning-based approaches. Here's an example task within the realm of natural language processing, and this is referred to as sentiment analysis. So in this task, given a text review written on let's say, a reviewing website, we'll denote that review as X, and the task is to determine whether the sentiment contained within this textual description is negative, neutral, or positive. So here's a simple example. So if somebody writes, "I do not like this movie," this review is clearly expressing a negative sentiment. If somebody says, "I love this movie," then that's clearly representing a positive sentiment. One thing that's noteworthy about this task is that the input that we need to process, namely the paragraph X, this is of variable length. Although in this case, the output is of fixed size. It's a classification of negative, neutral, or positive. So one classical way to solve this task is through a bag of words, a BOW model. A bag of word model makes the prediction with a linear combination of tokenized words. This is an extremely simple baseline, and roughly this is how it would work. For each word, we have the word assigned to a particular one-hot vector. A one-hot vector is a vector that contains all zeros except for a single coordinate that has the value 1, and this single coordinate value of 1 is referred to as the one-hot element. So each word, based on its dictionary order, is assigned a position, a one-hot vector. And then for the bag of words model, you combine all of these words into their corresponding one-hot vectors. You add these vectors, and then you multiply that added vector you take an inner product of that added vector with a certain weight vector. So the one-hot vectors will have a certain dimension, which we'll write as dimension n. The weight vector will have dimension n, and then we'll also add a bias, and the output becomes a score. So maybe if the score is sufficiently positive, then that corresponds to a positive sentiment. If the score is sufficiently negative, then that corresponds to a negative sentiment. And if the score is sufficiently close to 0, then maybe that refers to a neutral sentiment. In this BOW model, the weights, the n coefficients within the weights, and the bias scalar, these n+1 parameters would be the trainable parameters. More generally, the notion of bag of words refers to models that view a sentence as an unordered collection of words. So the metaphor is that you have a bag and you have a bunch of words in them, and if you mix up the bag, well, you still have the collection of words, but you are not concerned with the order in which the words appear. Now, this is a problem because this is a nice and simple way to do things, but the issue is that completely disregarding the word order in natural language is a significant drawback. A lot of meaning in our natural language is determined by the precise order in which the words appear. So when you ignore the order of the words, well, there's a lot of information that gets lost. Let's define some basic notation for these lectures. So we'll define this sequence notation. The word sequence will often be abbreviated as seq. So let U be any set, then a k-tuple of the set U is a set that looks something like this. So you have a bunch of U's, U1 up to UK, and you put them together as an ordered list. So that is the set of k-tuples. So for the sake of specificity, you can think of U as the set of, let's say, letters within the alphabet or words within a dictionary. So if you have a K tuple of letters, then you have a sequence of letters of length K. And then if you have a K tuple of words, then you have a sequence of words where you have K words. The clean star notation looks like this. So this is U star. And this is defined as, well, this union. And this union notation might seem unnecessarily sort of mathematically sophisticated, but what this just really means is this just denotes the set of U's of arbitrary finite length. For the sake of specificity, if you were to let the set U be the set of alphabets, then the set U star would denote a sequence of letters. Elements of U star can be length 0. So the empty sequence is an element of this U star clean star set. And there is the requirement that the sequence length be finite. And in the context of natural language processing and language modeling, we don't want to deal with infinite sequences. So the requirement that the sequence length is finite is exactly what we want. We will denote the sequence of characters with this calligraphic C. So this set C can be the set of, let's say, English characters, space, and some punctuation, right? So only containing the English letters is obviously not enough. You need at least you need to at least express a space at the bare minimum. But in a more expanded set of characters, the set C could be the set of all Unicode characters. So X is equal to C star. This will be the set of finite length sequences of characters. And well, if you think about what text is, this set X equals to C star, that is the set of text that we will be processing in language modeling. I will just quickly point out that the definition and scope of a character is actually not obvious, and different choices represent different trade-offs. So the modern approach is to view each byte within a Unicode encoding to be the indivisible basic unit. And I'll come back to this point again when we talk about byte pair encodings. In modern natural language processing, we process text with neural networks. And neural networks perform arithmetic on vectors and numbers. So at some point within the pipeline, the text has to be converted to a set of vectors. And that's what a tokenizer does. The tokenizers convert text into a sequence of vectors for the neural network to then go in and process. So given a text X, in this case expressed as a sequence of characters, a tokenizer is a function that takes in a sequence of characters, a text, and produces a set of vectors of length n. So the tokenizers that we will consider will output a sequence of vectors of uniform length. So that's what this notation means, RN star. So given the input text in this notation, the output will be a vector U1. A U1 will be of length n, and then the subsequent vector U2 will also be of length n, and the final output UL will also be of length n. So all of these vectors will be of equal length. They will all be of length n. Now, the input characters, in this case, the input text consists of big T characters. And then the output after the tokenization, the output vectors will have length L. So in total, there's going to be N times L numbers represented in the output. But in the tokenization process, there is no requirement that T, the input character length, and L, the output vector length, there's no requirement that they be the same. The input character length T also does not have to be equal to N times L. It's usually the case that the number of output vectors is smaller. The sequence length gets smaller compared to the input character length. Sometimes the tokenizer tau, which we denote as tau, is fixed. Sometimes it is trainable. For example, the word-to-vec tokenizer is an example of a trainable tokenizer. And for text generation, we will want the tokenizer to be invertible. I'll come back to this point when we talk about text generation. Okay, so let's think about some basic options for tokenization. Let's first consider a character level tokenizer. And for the sake of simplicity, let's assume that the character set consists of all the English lowercase letters, no uppercase, just space, period, question mark, and exclamation mark. So the bare minimum punctuation and only the lowercase letters. And let's think of the tokenizer that takes in as input text, which is a sequence of characters, and we tokenize each characters individually. where each tokenizer, when the tokenizer applied to each character, outputs, well, if A goes to 1, B goes to 2, and then Z goes to 26, and the remaining special characters take on numbers like 27, 28, 29, etc. So if we do this, then the output of the tokenizer is a scalar, so we should regard that as a vector of length 1. And then the output sequence length L is the same as the input character sequence length T. So this is a simple idea, and I would say this is not a bad attempt, but it turns out that this doesn't work very well. So it turns out what we actually want is we want the distinct tokens to be mapped to vectors of distinct directions. And that is because it turns out neural networks are better at distinguishing directions rather than distinguishing different magnitudes. So here's a better version of a character level tokenizer. So we have the same character set, and what we do is, well, we tokenize the individual characters individually, but now all of the letters and all the punctuation marks, they get mapped to a one-hot vector. Now, this character set has 30 possible characters. So in order to map them all to distinct one-hot vectors, we would need the output to be one-hot vectors of length 30. So the output vector is now length 30. In this case, the output sequence length is the same as the input character sequence length. Another option is to consider a word level tokenizer. So for the example, for the sake of simplicity, let's say the character set is just only the lowercase English letters and only the space, so no other punctuation marks. And then our setup, let's define W to be the set of words as, let's say, given by the English dictionary. And let's assume, for the sake of simplicity, that within our text, there are never any misspelled words. So then, the way the tokenizer works is it takes in as inputs a sequence of characters, but we can reinterpret that as a sequence of words separated by spaces. Then the tokenizer acts on these words individually, and each word is mapped to a distinct one-hot vector. So in this case, n, the output length of the tokenizer, it has to be equal to the number, to be the cardinality of the set W, which is the size of the dictionary. So the number of words contained in your dictionary, that's going to be equal to the output one-hot vector size. In this case, for this kind of tokenizer, the output sequence length L is going to be much shorter than the input character sequence length T because, well, most words consist of more than one character. So if when we do a word level tokenizer, the output sequence length does get shortened quite a bit. Again, with the clean star notation and all, we will be considering sequences of finite length. And to terminate a text sequence, we're going to use the so-called end of string token. So given a sequence of characters x, which has length t that is assumed to be finite, we will equivalently consider a special end of string token, which we'll write as EOS, to be the final t plus 1th element. So in other words, if x is a sequence of length t, considering of normal tokens, C1 up to CT, well, that's going to be the same as the sequence containing C1 up to CT, and then a special end of string terminal token. And for any element within the set U star, we're going to use a similar kind of notation. So here's a quick discussion on these kind of tokenizers. Question, what is the advantage of a word level tokenizer over a character level tokenizer? So the advantage is that you get a shorter tokenized sequence. And another advantage of the word level tokenizer is that it actually utilizes the dictionary. So that means the model does not need to learn all the words from scratch. By grouping characters together into words and using that information, a word level tokenizer can allow the model to learn things much more quickly compared to a character level tokenizer. What's an advantage of a character level tokenizer over a word level tokenizer? Well, a character level tokenizer can learn to handle misspellings and inflections. It's also much better for multi-language models because the size of the dictionary for just the English language is actually quite manageable in the modern era with our large amount of compute powers. But if you are considering 30 or 100 distinct languages and you want to put the dictionaries all together, the collection of all dictionary entries in all of these multiple languages, that number turns out to be a bit too large. Next question, are there other tokenizers that we have not yet talked about? The answer is yes. So word2vec is a trainable word level tokenizer. I'll talk about that later. And then there are what's called sub-word tokenizers, such as byte pair encoding. These are also trained tokenizers, but this is doing tokenization at a level smaller than a word, hence the terminology subword, but it is larger than a single character. I'll talk about the byte pair encoding tokenizer later. So let's revisit the BAO implementation, the bag of word implementation. So let tau be a word level tokenizer with our dictionary W. Then we can write an input sequence X as a sequence of words. And what the BAO model does is it takes the input sequence, the input text X, decompose it into a sequence of words, apply the tokenizer on the individual words, take the inner product with A, and then add the bias term B. And this is the same architecture description that we had a few slides ago. And the set of trainable parameters is the vector A and the bias term B. So there are n+1 trainable parameters. As I said, the BAO model is a very simple model, and the modern state-of-the-art NLP methods, they are based on deep neural networks. So really what's going to happen is the sequence of words along with the end of string token is going to be input into some complicated neural network, and the classifier is going to do something with that. Okay, so let me introduce the next task, language modeling. So a language model, which is abbreviated as LM, of course, when a language model is large, then we refer to that as a large language model, but we'll get there one step at a time. So a language model achieves one or two of the following goals. The goal number one of a language model is to assign probabilities and likelihoods to sentences. Goal number two, generate likely and coherent sentences. So this is goal number one. So we have some complicated neural network, text goes in, and the language model is to output a probability as to how likely, how probable this sentence is. In goal number two, we have this neural network, we input the text, and then it goes on to generate a coherent sentence, coherent text that completes the given input partial character sequence. So the best things I have ever done, one, traveling to different countries, yada, yada, yada. So these are the two goals of a language model. And I would argue that the question of why a language model is useful was not at all an obvious question prior to the era of ChatGPT. I mean, if you have a language model, you can assign likelihood to sentences, but like, how would you, like, what would you do with that? You can generate text, but if the thing just talks to itself, it just generates like words, why would that be useful? As a quick remark, this definition of a language model, it excludes encoder-only transformer models such as BERT, but let's not be overly concerned with these precise definitions. So actually, one very nice use of a language model is in constructing a voice-to-text system. So in a voice-to-text system, you can have multiple interpretations that can be auditorially ambiguous, but semantically not at all ambiguous. And a language model can determine which interpretation is more likely. Okay, let me read these two sentences. Sentence number one, the parcel was secured by gray tape. Sentence number two, the parcel was secured by gray tape. Now, I would argue that that is auditorially ambiguous, but if you were to hear that kind of sentence, you would, as a human, you would always pick out the first interpretation because obviously the second interpretation doesn't make any sense. So without any conscious thought, you're going to hear the voice as this first sentence. Let me read these two sentences. Sentence number one, he was a lighthouse keeper. He was a lighthouse keeper. I mean, again, if you really accentuate where the space is supposed to be, you can try to distinguish these two sentences, but really this is ambiguous. But under normal circumstances, you would hear the first sentence. And nowadays, a lot of the smartphones have some sort of voice-to-text system. And all of these voice-to-text systems will have some sort of language modeling component because a voice-to-text system has to resolve this kind of auditory ambiguity between two different interpretations. And the only way to do it is to feed these two interpretations into a language model and to ask which one is more probable. You also have a similar kind of application when it comes to spelling correction. Another application of language models is autocomplete. So an autocomplete system can assist writing by suggesting likely completions of a sentence. So in your email client, I'm sure you've seen something like this. And well, how does your email client know what kind of completion is more likely? Well, it's relying on a language model. Another application of language model is SSL pre-training and universal interface. So training a neural network to be a language model is a useful pre-text task for transfer learning in the sense of self-supervised learning, SSL. So what you do is you pre-train a language model on a large corpus of text, and the resulting model is referred to as a foundation model. And then you take that pre-trained model and then you fine-tune it on some sort of downstream task. Maybe you fine-tune it on sentiment analysis. Maybe you fine-tune that model to be a translation machine. There's some downstream task. To accomplish it, you use the pre-trained foundation model. This approach is something I'll talk about further in detail when we get to the ELMo, BERT, and GPT-1 models. However, yet another application is if you have a sufficiently powerful language model, this can serve as a universal language-based interface to the capabilities that the language model has learned. So actually, when you're communicating with other humans, let's say you hire a human assistant and there are a wide range of tasks you want your human assistant to accomplish. And the interface between you and the human assistant is through natural language. If there's something you want your human assistant to do, you communicate that in natural language. There's no special computer API to do that. There's no form that you need to fill in. You can just talk to the other person and they will understand what it is that you want. And the same can be said for the sufficiently powerful modern large language model based chatbots. So we'll talk about this more when we talk about the T5 and GPT-3 models, but the idea is that if you have a sufficiently powerful language model, you can just say what it is that you want and it will do it for you. Next, let's talk about assigning probabilities to sequences. So let's assume we have a sequence of U's, U1, U2 up to U big L. And if we assume that the sequence is generated randomly, well, that means we're going to assign a probability on the generation of the sequence. So the probability of the sequence being generated should be a number between 0 and 1. When considering these random sequences, the sequence length big L itself should also be considered a random variable. Imagine the sequence U1, U2, dot, dot, dot being generated sequentially. If we have a partial sequence, U1, U2 up to U little l, then the next token that is being generated, UL plus 1, could be the end of string token. If it is the end of string token, then the sequence terminates. If it's not the end of string token, if the subsequent token is something else, then the generation continues, and then the generation would continue on to the subsequent token, UL plus 2. And here's a minor but necessary clarification of notation to make. So let's say a big L is our sequence length. Then the probability of this sequence, if I'm denoting it this way, what I'm referring to is the probability of this sequence U1 up to U big L being generated, and also the sequence terminating right then and there. So this is the probability of the random sequence having values U1, U2 up to U big L for the first L elements, and then terminating then. On the other hand, if I were to write U1, U2 up to U big L and use this notation without the double parentheses, then with this, I'm denoting the probability of the random sequence having values U1 up to U big L, but we are not talking about whether the UL plus 1th token is the end of string or not. So this event that we're assigning the probability to is not determining whether the sequence is terminating right there, then and there. So to clarify, a PU1 of U up to U big L would be split into two events. One event is where UL plus 1 is the end of string token, and then UL plus 1 is not the end of string token. When you have the generation of a random sequence, you can decompose the probabilities via the chain rule, the conditional probability. You can decompose it into the generation of each individual token. So here we have the probability of the sequence U1 up to UL, including the event that at UL plus 1 the sequence terminates. This can be decomposed. We can first of all pull out the probability of UL plus 1 being equal to the end of string token conditioned on the past, and then we can write the probability of the first L token values. Then these token values can all further be decomposed. And if we do this recursively, then we have a product of these probabilities. These probabilities individually quantify the probability at token position 1, token position 2, token position 3, up to the terminal token, token position big L plus 1. To clarify, in this decomposition where we decompose the probability of the entire sequence into a product of the individual token generations. Here, we have made no assumptions, absolutely zero assumptions on the distribution of the sequence probabilities. So we have not made anything like a Markov assumption. We have not assumed anything is independent. This conditional probability decomposition, it holds always. Here's a minor comment with conditional probabilities on continuous sequences. So if the sequence elements that we consider in our random sequence, if these are continuous random variables, then we need density functions instead of discrete probability mass functions. However, things are basically the same. So if you want to work with sequences with continuous values, then you just basically all the calculations go through essentially in the same way, but you just need to replace mass functions with density functions. When you're working in the domain of natural language processing, the vocabulary tends to be finite, so we can consider sequences with discrete elements. For some reinforcement learning problems, the state spaces and rewards, those can be continuous. So, and if that's the case, then you may want to consider sequences with continuous values. To clarify, what I'm talking about here is the notion of time or the notion of sequence position that is still discrete. But what I'm rather talking about is whether the sequence values can take on the continuum of continuous possibilities or rather a set of discrete possibilities. We will later see that in vision transformers, images are processed, are converted into sequences of patches, and they are processed with sequence-to-sequence models. For these vision transformers, the image patches are better understood as vectors that take continuous values. So when you analyze vision transformers, you would want to consider them to be sequence-to-sequence models with continuous sequence values. An autoregressive AR model of a sequence learns to predict the subsequent element UL given the past observations U1 up to U little l minus 1. The goal is to learn a model f sub theta that approximates this full conditional distribution. So here is the exact full conditional distribution. Given the earlier sequence elements, U1 up to U little l, there's a probability, there's a conditional probability on U little l, and we want our neural network f theta, our model f theta, to approximate that. And let's say we were somehow able to train an autoregressive model well. So f theta now is a good approximation of this conditional distribution. Then, using this model, we can approximately compute the likelihood of a given sequence. So given a random sequence, the probability of its generation is exactly equal to this product of conditional probabilities, and we can approximate that as a product of these model f theta evaluations. And if we have a trained autoregressive model f theta, and if we have an unterminated partial sequence, so if we have elements u1 up to ul little minus 1, then we can continue the generation. We can perform text generation using this autoregressive model. Namely, we can generate the subsequent values, u sequence elements u1 up to u big L, by performing sampling in accordance to this model f theta. Namely, we plug in the earlier elements u1 up to ul minus 1, and then that defines a probability distribution on the subsequent token. And then we perform the generation in accordance to this probability distribution. Now, this autoregressive generation is justified by this product of conditional probabilities. Again, conditioned on the given input partial sequence, u1 up to ul minus 1, the distribution of the subsequent tokens can be decomposed as a product of these conditional probabilities, and that can be approximated as a product of these f theta evaluations. So if we perform the generation in accordance to this distribution, namely if we generate one token at a time going forward, starting at ul minus 1, according to this rule, then that would approximate generating from the actual probability distribution of the sequence. In modern natural language processing, a wide range of natural language tasks, including language modeling, is solved using deep neural networks. To do this, we need a general approach to process sequences which are of variable length, both as inputs and outputs. We'll start by considering RNNs, and then we will move on to the transformer architecture. Now, why should we still learn about RNNs? So you may be aware that modern language models are all built using transformers, and RNNs are really no longer used, at least not in the mainstream. Indeed, that's the case. Transformers have been replacing RNNs and CNNs in recent years. But nevertheless, much of the architectural design of transformers are inspired by practices inherited from the RNN era. So in my view, you still need to know RNNs to fully understand the motivation behind a lot of the components within a modern transformer. Okay, so let's talk about learning with variable-sized inputs. For comparison, in image classification, the neural network takes in as input a color image, and so that would be a 3 by n by m tensor. This is an input of fixed size. And traditionally, such an input is processed by a deep convolutional neural network. In contrast, in natural language processing, we want to process a variable-sized input using a neural network. So here's one simple idea. If you have various inputs, so let's say you have input x1, x2, and x3, these are tokenized to be sequences of length 4, 3, and 5. So the tokenized sequence length is not uniformly the same. If you have these different sequence lengths, you can pad them up, pad up these shorter ones so that they all reach the length of the longest sequence. So for example, for the second sequence, which is of length 3, we perform zero padding at the end to make it length 5. Now, this is perhaps not a terrible idea, and this can certainly work as a quick and temporary solution. However, this simple approach has some downsides. So one downside is that this does not scale well for long sequences if we're using fully connected layers. So this padded input sequence will have a certain length. If we process that with, let's say, a fully connected layer, we would have to process a very long sequence with a fully connected layer. That's a lot of computation. That's also a lot of trainable parameters. So that would be inefficient. Another problem is that this approach requires the specification of the maximum length. So if we have an input sequence that is longer than that set maximum length, then this approach just wouldn't work. So then as our next idea, we can process one input per layer. So again, consider this example where we have three input texts, so x1, x2, and x3. These are tokenized into sequences of length 4, 3, and 5. So for the first sequence, we provide as input the first sequence element, and we also provide the initial hidden state, which is usually initialized to be 0, and a single layer processes that information. This produces the subsequent hidden state, which is passed on to the next layer. The next layer also takes in as input the next sequence element. So this layer processes that. That produces the next hidden state. This next hidden state and the next sequence element is processed by this next layer. This again produces a hidden state. The next layer processes that together with the next sequence element, and then that produces the result. If you have a sequence of length 3, then you have 3 steps of processing. If you have a sequence of length 5, then you have 5 steps of processing. We can express this idea in functional form. So at every layer, we have the previous hidden state and the current sequence element, and that's concatenated into a longer vector. We pass that through a linear layer. So the linear layer at sequence position L has the linear term A sub L and the bias term B sub L. Then we pass that through a nonlinear activation function to get the subsequent hidden state. So this is a nice idea, and it has some advantages. One advantage is that shorter sequences require fewer layers to evaluate. So shorter input sequences require a smaller amount of computation, and it's only when you have a longer sequence that you have to pay the larger compute costs to process the longer sequence. Another advantage is that each layer is much smaller than a single giant layer that you would need to process the whole sequence at once. So at every sequence position, we have this linear layer that processes the previous hidden state and the current sequence element. And this is a much smaller vector compared to the entire U sequence. However, there's still some downsides. So one is that the total number of weights and biases increase with the maximum sequence length. So A sub L, B sub L. So these are the trainable parameters at sequence position L. And if we have many sequence positions, then we will have many of these trainable parameters. Another issue is that we have exploding and vanishing gradients with this approach. I'll explain this point further soon. So then let's try to resolve this issue of having too many trainable parameters proportional to the maximum sequence length. The idea is to use weight sharing, and that means we're going to share the same parameter for all of the layers. So in functional form, what we do is each layer processes the previous hidden state and the current sequence element. We concatenate that and pass that through a linear layer. But note that in this linear layer, this is A without a subscript, and this is B without a subscript. In the previous slide, we had almost the same equation, but there used to be a subscript. So this used to be A sub L. This used to be B sub L. So we simply deleted the subscripts. And if you look at the diagram, the meaning of this is that at every step of processing, we use the same A matrix and B bias vector for all of the layers. So this is a nice idea. We've reduced the number of trainable parameters, and now we're also able to process an arbitrary number of inputs. No matter how long the input U sequence is, this equation is going to be well defined. We still have the problem of exploding and vanishing gradients, but I'll get to that soon. So this overall approach is referred to as a recurrent neural network, an RNN. More generally, a recurrent neural network, an RNN, has this form where we have this initial hidden state, usually initialized at 0, and the subsequent hidden state is obtained by applying the recurrent function q sub theta tilde to the previous hidden state and the current input vector u sub l. And then after all of this processing for the final output, we denote the final output as f sub theta applied to the input sequence x. We compute that by applying a linear layer to the final hidden state h sub l. So h sub big L, that's the final hidden state. We multiply that by the matrix A and then add a bias vector B. And then we denote theta for the set of trainable parameters, the matrix A and the bias B used at the final output, and the parameter theta tilde that goes into the recurrent function. So this is a general form of an RNN, and the exploding and vanishing gradient problem still needs to be resolved. And in fact, an RNN can work only if the recurrent function q sub theta tilde is chosen to mitigate this exploding and vanishing gradient problem. So then what is this exploding and vanishing gradient problem? Well, the problem arises because RNNs are extremely deep networks. In natural language processing, processing sequence lengths of hundreds or thousands is quite common. So that is to say, you should think of this sequence length capital L as a number, let's say, on the order of thousands. Now, to perform training of this RNN, you need to perform backpropagation. And if you work out the backpropagation calculation by hand with respect to this parameter theta tilde for the recurrent function, it comes out to be this. And this red term, DLDH little l, based on the chain rule, it can be expressed as DLDH big L, DHL minus 1, ... So we have a product of these terms. Now, to be precise about what this means, H is a hidden state vector. So DHL minus 1, this is a Jacobian matrix. So this product is a product of Jacobian matrices. But for the sake of simplicity, for the moment being, let's think of this as a product of scalars rather than matrices. Now, if you multiply a lot of scalars, and again, think of big L as something on the order of thousands, and let's say little l is half of that. So this is a product of, let's say, 500 numbers. When you're multiplying a lot of numbers, that tends to be quite unstable, because if most of the numbers that you're multiplying are larger than 1 in magnitude, then the product quickly blows up to plus infinity. And in this case, you would get the exploding gradient phenomena, where you get gradients of huge magnitudes. Sometimes this can be dealt with the gradient clipping mechanism, which I'll talk about in the next slide. On the other hand, if most of the numbers that you're multiplying have magnitude less than 1, then the product very quickly converges to 0. When this happens, you have the vanishing gradient phenomenon. And when this happens, you really don't have a good gradient signal, because not only is the magnitude of the gradient small, the direction of that gradient tends to be unusable. So if we want this large product to result in a reasonably sized result, the numbers must all have magnitude close to 1. Now, going back to the actual meaning of this, again, this is a product of Jacobian matrices, not scalars. But if you consider a product of matrices, a similar kind of reasoning holds if you replace the notion of magnitude for scalars with eigenvalues or singular values of the Jacobian matrices. So again, you have the exploding gradient problem when the gradient magnitude becomes very, very large. When you have an exploding gradient, that implies that the output is very sensitive to small changes of the parameters in a certain direction. And sometimes these kind of gradients are unworkable, and the only way to fix things is to use a different neural network architecture. And to further comment on the second point, in machine learning, in deep learning, the optimization problem at hand is usually not fixed. Usually, the optimization problem, the optimization landscape that you're dealing with, is a function of the choice of the neural network architecture. So in machine learning, if you have a difficult optimization problem, often a good way to resolve this issue is to change the neural network architecture. In the context of RNNs, this might mean using something like an LSTM cell, which we'll talk about soon, or maybe ditching RNNs altogether and using a transformer architecture. In any case, going back to the exploding gradient problem, sometimes when you have exploding gradients, the magnitude is too large, but the direction of the gradient might still give you useful information. So if this is the case, then we can use gradient clipping and use the clipped gradient in the optimization. The functional form of gradient clipping looks like this, and the interpretation is that we will compare the magnitude of the gradient with a certain threshold. Now, if the magnitude of the gradient is smaller than the pre-specified threshold, then we don't have exploding gradients, so we will just use the gradient as is. But if the magnitude of the gradient exceeds this threshold, then we keep the gradient direction, but we shrink the gradient magnitude to be equal to this threshold v. So that's what we mean by clipping the magnitude. So we are keeping the gradient direction, but we are clipping the gradient magnitude. So here's an illustration of a problem that can happen when you don't use gradient clipping. So here we're performing the optimization and we go downhill. And then at this point, we take a little step, but this takes us way uphill. And then on this hill, the optimization experiences a very large gradient magnitude. So the update flings the parameters to way far away, and then the optimization is kind of ruined. With gradient clipping, this doesn't happen. So the optimization would proceed more steadily. And even if we were to climb up this hill and experience the large gradient magnitude, we would gracefully come back down. The vanishing gradient problem, on the other hand, occurs when the magnitude of the gradient is very small. So intuitively, vanishing gradients mean that the gradient signal does not reach the earlier layers. So in an RNN, for example, DLDHL, DLDH big L may not be small, but DLDH little l could be small. So again, based on the chain rule, DLDH little l is DLDH big L times DH big L DHL minus 1. So we have a product of these Jacobian matrices. And even when DLDH big L is not small, if these other terms were small, then DLDH little l, this can be small. Now, if we go back to this diagram, the interpretation of that scenario is that this output would change if this final hidden vector would change. But if this earlier hidden vector changes, that doesn't really affect the final output. This means small changes in h little l, an earlier hidden state vector, does not affect the final loss. And since DLDU little l is DLDHL, DHLDUL, this further implies that small changes in u little l does not affect the output loss. So again, going back to this diagram, if the final loss isn't really affected by the value h little l, in this case, let's say h2, well, u2, the sequence element u2, affects the output only through this hidden vector h2. So if the output is not really affected by changes in h2, well, if we change u2, u2 is going to change h2, but that change is not going to really propagate to the end to affect the final output. So we can intuitively understand this phenomenon as the RNN not really utilizing the information u sub l. In other words, the RNN does not remember u sub l by the time it reaches the final processing stage, big L. Moreover, the gradient signal DLDH big L is lost by the time backprop reaches the time step, the sequence position little l, and the model can't learn to utilize u sub l. So the model forgets u sub l by the time it reaches the terminal step big L, and furthermore, the gradient updates will not be able to fix this. So we need to promote better gradient flow. So again, let's look at this chain rule formula. DLDH little l is DLDHL plus 1, DHL plus 1, DHL. We say that if this Jacobian matrix is close to identity, so DHL plus 1, DHL, this is equal to the derivative of the recurrent function with respect to the hidden input h. If this Jacobian matrix is close to the identity matrix, then we say that the gradient flows through this layer well. Conversely, if this Jacobian is close to 0, well, then this product will be close to 0. And in that case, we say that the gradient does not flow well through the layer HL plus 1, because any gradient information contained in this term is going to be lost, because whatever this is, well, we multiply it by 0, so the gradient DL/DHL is going to be close to 0. So then, do we always want to have good gradient flow? Do we always want DHL plus 1 DHL to be close to the identity matrix? Well, the answer is actually no. So we want this Jacobian matrix to be close to the identity only when we want to remember information. And we're not trying to build a machine that remembers everything. We're trying to build a machine that processes information. And the act of processing information is not merely remembering information. Sometimes you need to forget information that you deem unnecessary. So we want the Jacobian matrix to be close to 0 when we want to forget. So the solution is to design a sort of neural circuit that explicitly controls when to remember information and when to forget information. So shown here is an example of such a circuit. So as input, we have this cell state, CL-1, and in the end, it will produce the subsequent cell state, CL. We're going to take this cell state and multiply it by this so-called forget gate. So F is a value between 0 and 1, and we'll perform element-wise multiplication. And after that, we will add this G term to add new information. So the functional form of this is CL is equal to CL-1 element-wise product FL plus G. And if we compute the derivative DCL-1, this comes out to be F. So depending on what the value of F is, we can make the Jacobian matrix equal to the identity matrix if the values of F are all equal to 1, or we can make the Jacobian matrix exactly equal to 0 if the values of F are all equal to 0. So this idea leads to the design of LSTM cells. LSTM is the abbreviation of long short-term memory, and it has a somewhat intricate structure, and parts of it feel, admittedly, a little bit arbitrary. So the LSTM cell was originally published by Hochreiter and Schmidhuber in 1997, and then in 2014, Chung et al. Presented the GRU cell, which simplifies the LSTM structure. And the success and effectiveness of the GRU cell implies that indeed some of the components of the LSTM cell are arbitrary and redundant. Nevertheless, the LSTM cell has historical significance, so let's go through its design one component at a time. The LSTM cell takes in as input the previous cell state, CL-1, and the previous hidden state, HL-1. It also takes in as input the current sequence element, UL. So the current hidden state and the current sequence element are concatenated, and then that is passed through a linear layer defined by the weight matrix W and the bias vector B. That produces an output, and we chunk that into 4 equally sized components, and we refer to those 4 components as F bar, I bar, G bar, and O bar. So here's the path that F bar goes through. F bar then goes through an activation function, the sigmoid activation function, and that results in the F vector. The F vector is referred to as the forget gate, and this being an output of the sigmoid activation function has values between 0 and 1. And the forget gate is used to modulate the previous cell state. So we have this previous cell state, we multiplied element-wise to this forget gate, and then later we add on new information to get the subsequent cell state. Next, here is the path for the I bar vector. It goes through the sigmoid activation function, and that results in the I vector. Again, the I vector being an output of the sigmoid activation function has values between 0 and 1, and the I vector is used to modulate this G vector. Next, this is the path for the G bar vector. This G bar vector is passed through a tanh activation function, and that results in the G vector. The G vector being an output of the tanh activation function has values between -1 and +1. It is element-wise multiplied to this I vector, so the I vector serves as modulating this G vector information, and then that is added to here to produce the subsequent cell state. This is the path for the O bar vector. It is passed through the sigmoid activation function, and that results in the O vector. O vector, again, being an output of the sigmoid activation function, has values between 0 and 1. And then we take the output cell state, we feed that through the tanh activation function, and then we have that output be modulated by this O vector, and that results in the subsequent hidden state H sub L. The LSTM cell is designed to promote better gradient flow, and because of this, this works much better than a naively designed RNN. Within LSTM, it is the cell state that really serves as the memory unit. Now, in retrospect, the cell state C probably should have been called the hidden state because the cell state is more similar to the hidden states of an RNN or the hidden state of Markov models. But nevertheless, referring to this the cell state as the cell state, the hidden state as the hidden state in this way is now standard terminology, so that's what I'm going with. Sometimes you want to use the LSTM to output a large hidden state while maintaining a reasonably sized internal computation. You would want to do this in language modeling, where the output size can be equal to the vocabulary size or the number of tokens when you use byte pair encoding, and this is a relatively large number. So the solution is to use LSTM with output projection. So the LSTM cell with output projection looks very much similar to the LSTM cell without output projection, but we have this additional output projection operation. So in the vanilla LSTM, this output served as the hidden state, H sub L, but in this version of LSTM, we'd feed that through a linear layer that produces a hidden state H sub L with a larger dimension. Now, by design, the C vector, the FF vector, the I vector, the G vector, the O vector, these must have the same dimension. So these will have a smaller dimension. So the internal computation that goes on in here, that has a much smaller dimension, while the hidden state H has a larger dimension as needed. To clarify, the name long short-term memory is not referring to long-term memory and short-term memory. Rather, it means that the cell states serve as a longer short-term memory. So note that there's a hyphen here and there's no hyphen here. So it's a longer short-term memory. And in contrast, a naive RNN that would use an MLP rather than an LSTM cell as a recurrent function, a poorly designed RNN would have a much shorter long-term memory. So the claim made by the name LSTM is that this LSTM cell is going to work better than the naively designed one because the short-term memory mechanism of LSTM is better. The short-term memory mechanism will last longer, and therefore this should work better. A true long-term memory would correspond to using some sort of external storage, and this is something an LSTM RNN doesn't have. But now, in the year 2025, proprietary LLMs do have long-term memory. Here's an announcement tweet by OpenAI announcing this feature, and here's the research scientist Noam Brown providing commentary on this new long-term memory feature. He says, memory isn't just another product feature. It signals a shift from episodic interactions, think a call center, to evolving ones more like a colleague or friend. Still a lot of research to do, but it's a step forward fundamentally changing how we interact with large language models. As an aside, the exploding and vanishing gradient problem is something that arises in deep neural networks, not just RNNs. For comparison, if we go back to the year 2012, the AlexNet architecture was published, and this great success was followed up with a lot of effort to train deeper and deeper neural networks. The VGG architecture and the GoogleNet or the GoogleNet architecture were presented as deeper neural networks with greater success, but efforts to train further deeper versions of these architectures failed because precisely of the exploding and vanishing gradient problem. And then the ResNet architecture was presented, showing that the use of residual connections is a way to mitigate the exploding and vanishing gradient problem. Another key technique was the use of normalization layers such as batch norm. Now, with residual connections and batch normalization, people are able to train much deeper neural networks for image classification with depth, let's say hundreds or even thousands. RNNs have the exploding and vanishing gradient problem along a slightly different dimension. RNNs have this problem along the sequence length dimension. And one might ask, can we use normalization layers to resolve this issue? And indeed, there has been some effort, some research trying to use, let's say, batch norm to resolve this problem, but it seems to not have worked well enough to become common practice. So let's talk about some tasks we can perform with RNNs. So first, we have the sentiment analysis. So here we have the sentence, the hamburger was good. And the task at hand is to determine whether the sentence is representing a positive or negative sentiment. We can do this with an LSTM RNN. So the words are tokenized one at a time, and these tokenized words are fed into this into the RNN cells. And at the end, we extract this hidden state and pass it through another linear layer to produce the scalar prediction as to whether the sentiment is positive or negative. In performing this classification, it makes sense to extract this final hidden state because this hidden state depends on the entire sentence, and you would think that determining the sentiment of the sentence would require seeing the entirety of the sentence. But it turns out that you can improve the performance by using not just the final hidden state, but actually all of the hidden states. So the way you do it is you extract all of the hidden states at every sequence position, and then you pass them through a pooling layer, either an average pool or a max pool pooling layer, and then you pass that through a linear layer to perform the scalar classification. A consistent observation in deep learning is that deep neural networks outperform shallow neural networks. Now, arguably, RNNs already have an element of depth, depth along the sequence direction, but we can stack RNNs along the depth direction, and that will allow RNNs to learn more complex representations. So let's look through this diagram. At the beginning, we have the same RNN as before. This RNN produces a sequence of hidden states, and we take these hidden states and we use them in the next stack of the RNN layer as the sequence elements. So this hidden state, those are fed into the next stack of the RNN processing. So then this layer again produces a sequence of hidden states. We use those as the sequence inputs for the subsequent RNN stack. Finally, this produces a sequence of hidden states. We take those, we pull that, and then use that for the classification. In image classification, it's customary to train deep convolutional neural networks with depth hundreds and even thousands. And for modern transformer large language models, a depth count of 100 is customary. but stacked RNNs tend to work best with much modest depth count. So a rule of thumb is to use 2 to 8 stacked LSTM layers. So it's usually the case that using 2 layers is better than using 1 layer, but using 3 layers is not always better than 2. So what you would want to do is you would want to try 2 layers and then try to increase the layer count one at a time and tune the depth as a hyperparameter. And when you're looking at this kind of stacked RNN, you should view each layer of this RNN as a transformation of a sequence to another sequence. So in this example, we have this input U sequence that gets transformed to a sequence of hidden vectors. And then that a sequence of hidden vectors, they get transformed to another sequence of hidden vectors. Yet again, that gets transformed to another sequence of hidden vectors over here. And then these hidden vectors are pulled and then used for the classification. So every layer of the stacked RNN performs a sequence to a sequence transformation, where the input sequence gets transformed into another input sequence, while the sequence length, a big L, being preserved. Another NLP task that we can solve with LSTM RNNs is parts of speech tagging. In this example, we have the input sentence, he saw 2 birds, and we have the corresponding labels, pronoun, verb, number, and noun. And the goal of parts of speech tagging is to train an RNN such that at every sequence position, we provide an output of making the prediction what kind of parts of speech each word corresponds to. So in this task, the RNN is to provide an output at every sequence position, and the output at every sequence position incurs a loss based on its accuracy. So the final scalar training loss should be constructed as the sum of all the individual losses incurred at each sequence position. So far, we've talked about unidirectional RNNs that process information forward in time. However, in language, it's common for later words to provide the necessary context for understanding a previous word. So this kind of unidirectional processing is perhaps suboptimal. So a bidirectional RNN combines a forward and reverse directional RNN to process a sequence without a single sense of direction. So in this example, here, this is not a stacked RNN. This is a unstacked bidirectional RNN. So this bottom component of this RNN, this is simply a normal forward unidirectional RNN. And then this top component, which does not interact with this bottom component, is a reverse unidirectional RNN. So this top component processes the words in reverse order. So good, was, hamburger, that's the order in which the top RNN component processes the input. The forward unidirectional RNN and the backward unidirectional RNN, these two perform their processing independently. They produce a final hidden state each, and that's concatenated. And then finally, we pass that through a linear layer to perform the sentiment classification. And finally, stacking and bidirectionality can be combined. So really, if you're going to use an LSTM RNN, you should be using a stacked bidirectional RNN, and you should start out with a depth count of 2, and then you should increase the depth count 1 at a time to tune the depth as a hyperparameter. Language modeling is another task that can be done with RNNs. An RNN language model is trained as an autoregressive model with this following structure. The RNN takes in as input 1 word at a time, and then the hidden state is used to make a prediction on what the next word is going to be. For this time step, cat is the subsequent word, so that is fed into the cross-entropy loss, and the cross-entropy loss measures how close the prediction is to the ground truth next word. Then at the next time step, the subsequent word cat is provided as input, and the hidden state is then used to make a prediction of what the next word is going to be. The next word is sat, and the cross-entropy loss measures the accuracy of that prediction. The next word sat is provided as input to the LSTM, then the hidden state is used to make a prediction of what the next word is going to be. The next word is on, that is fed into the cross-entropy loss, and the cross-entropy loss measures the prediction against the ground truth label. So when training the language model, the LSTM outputs a prediction at every sequence position. So at every sequence position, a cross-entropy loss is incurred, and those cross-entropy losses for all these sequence positions are added up to form the final scalar training loss. So in functional form, this is what the training loss looks like. It's a sum of the cross-entropy losses at all the time steps. So for the training, we are given a sequence of tokens U1 up to UL. There's also the end of string token at position L+1. And then the RNN is trained to predict the next token, given the earlier tokens. So given tokens U1 up to U_l, the RNN produces the final hidden state. In this case, the hidden state at position l, and that is used to predict the next token UL+1. The accuracy and inaccuracy of this prediction is measured by the cross-entropy loss at all the positions. The sequence of length L, U1 up to UL, also with the end of string token at position L plus 1, this creates L next token prediction problems. Namely, you use U1 up to UL to predict the next token UL plus 1 for values of L1 up to big L. Now let's pay very close attention to the indexing. It doesn't really make sense to have the language model predict what the first token U1 is going to be, because what information would the language model have to be able to predict the first token? There's nothing. So the task of predicting U1 is not something that the language model is trained for. The language model is trained on predicting token U2, U3, U4 up to U big L, the final non-terminal token, and then also predicting the final end of string token at UL plus 1. So from position 2 to position L plus 1, those constitute big L next token prediction problems in total. And the final scalar training loss is defined as the sum of these L cross entropy losses. For language models, the training and the inference considers two materially different tasks. And it is instructive to view the distinction from an RL perspective. When you're training a language model, you are assigning probabilities and likelihoods to a given sequence via next token prediction. And you can think of next token prediction as being analogous to imitation learning. And training is done on real sentences written by human beings, so that defines the in-distribution data. The in-distribution data is sentences written by humans rather than via AI or language models. However, during inference, language models are often used to generate likely sentences and coherent sentences. And you can think of the generation as analogous to having a policy acting in the environment. Now, unless the language model is very good, the partial generations will have a slightly unnatural feel. And the generation conditioned on this kind of unnatural generation will be out of distribution because those kind of unnatural sentences that don't sound like they were written by human beings were not part of the training distribution. And therefore, the subsequent generation conditioned on this kind of unnatural generation will become worse. This is a consistent problem with acting on a policy trained solely on imitation learning. In the context of NLP, teacher forcing is the practice of feeding ground truth sequence values back into the RNN after each step, even though the RNN would not be able to generate such a natural sentence. And this is exactly like imitation learning. And teacher forcing forces the RNN to stay in the training distribution. However, as we've discussed in the previous slide, once a model makes a mistake, generates one bad token, the model really does not know how to recover because the model was only trained on the good text through teacher forcing or imitation learning. There are two ways to solve this. One is to start the training of the RNN with teacher forcing, because initially a randomly initialized RNN is just going to generate gibberish, so you have to use teacher forcing. So you start with teacher forcing, and then as the training progresses, as the RNN becomes better, you transition into something else. If you want to read more about what this something else is, you can read this paper by Bengio et al., published in 2015. And this other thing is called schedule sampling. I won't get into the details of it, but I'll also mention that in the context of language modeling, you can't really do something like Dagger to improve upon imitation learning. In the context of language modeling, if you were to do Dagger, what that would mean is you would have the language model generate a partial completion, and then you would have a human being come in and continue the language generation from there on. Now, there's two problems with this. One is that giving a partially generated paragraph to a human and having the human continue the generation is a very unnatural task for the human. But more importantly, the bigger issue is that even if you can find people that are willing and able to continue generation from a partially written paragraph, you would have to hire these people. And the hourly wage that you have to pay the humans to do this on demand would be prohibitively expensive. So the other approach is to just make the language model large and train on lots of data. And this lots of data should include both a very good and polished text and also poorly written and messy internet text with non sequiturs, grammatical errors, misspellings, etc. So because the language model is trained on lots of data, the generation just becomes better. The language model just becomes better. And also because the language model has seen a lot of poor text, the language model acquires a certain robustness and it is able to continue the generation even when the language model generation makes a mistake and generates a slightly unnatural or poorly written partial completion. So this is the solution that we have for modern large language models in terms of overcoming the limitations of imitation learning. The tokenizer is the first contact between language and our algorithm. You should think of your RNN and later your transformer as not interacting directly with the input language, the input text, but rather it's interacting with the sequence of vectors produced by the tokenizer. So it's important that your tokenizer is good. Your language model can work well only if the tokenizer is providing a good sequence of workable vectors. Now, one option is to do a word level tokenizer. So you could use a one-hot encoding with a fixed dictionary, but it's usually better to have some sort of trainable component in the tokenizer. Now, currently, byte pair encoding has become the standard choice, and we'll talk about that later. But for now, let's consider the historical context. So let's go back and think about, what does a word mean? Well, what do you mean what a word means, right? You have a dictionary, right? And that idea corresponds to denotational semantics. So a word is the collection of the objects it describes. A cat, it's not exactly obvious how you would write down a definition of what a cat is, but a cat refers to the collection of things that we refer to as cats. A chair is a collection of objects that we refer to as chairs. And love is a collection of emotions that we feel. And this is the intuitive and straightforward view of the meaning of words. But the problem with this is that it's not a very actionable definition, especially computationally. However, an alternate dual view is the notion of distributional semantics. So a word is characterized by the company it keeps. So a word's meaning is given by the words that frequently appear close by. So you should think of a word as having certain relationships with other words. The relationship between the word cat and dog will be different between the relationship between cat and tree. And the idea that a word is something that does something to another word, and therefore different words co-occur with different distributions, and the co-occurrence of these words is what really gives meaning to these words. This is the idea of distributional semantics, and it's a much more actionable notion in the realm of computational linguistics. So this is the idea that leads to word-to-vec. So we train a model such that a word predicts the neighboring word. So in this example, we have the center word into, and then it co-occurs with the word turning, problems, banking, crisis. We're disregarding the word ordering. We're just considering a context size, window size of 2. So these are the context words that occur within the vicinity of the center word into. And then for each word, we assign two vectors. We assign the v vector and the u vector. And this v vector for this word and this u vector for this word, these are trainable parameters of our model. And then for a center word wt and a context word wt plus k, so k would be within the window size, then the probability of a certain word occurring is given by the inner product between the center word's v vector and the neighboring word's u vector, exponentiated and normalized in the softmax manner. Specifically in word2vec, this is the loss function that is minimized. So for every single center word wk, we have a window size of n, and then we plug in the neighboring words, and we maximize the predicted log likelihood of the neighboring words, where the v vectors and the u vectors, those are the trainable parameters. So the insight is that we have two words, w and w tilde, and we consider these two words to be similar if the distribution of neighboring words of this w vector is similar to the distribution of neighboring words of this w tilde vector. So two words are similar if they have similar distributions of neighboring words. And under this construction of the model, this will happen if the v vectors are similar. And if you think about it, well, the word cat and feline are similar words. They're actually synonyms. And the distribution of neighboring words of cat and feline should be not the same. They're not the same word, but you can imagine that distribution being quite similar compared to, let's say, between cat and truck. Cat and truck are very dissimilar words. You would expect the distribution of neighboring words to be quite dissimilar between cat and truck. And it will turn out that the v vectors between cat and feline will be similar, and then the v vectors between cat and truck would be quite dissimilar. The goal of word2vec is to obtain a trained word level tokenizer. So given an input sequence of words, so X is chunked into words W1 up to WL, and if we have the trained tokenizer tau, which will tau theta, now we will write tau theta because now it's trainable, it will output the sequence of corresponding V vectors. So this is a data-driven way to map similar words to similar vectors. And now let's compare two options. Option number one is we don't do word to vec. Given an input text, we chunk it into words based on the dictionary, and then we assign a one-hot vector for all of those words. We feed those one-hot vectors into our RNN, and we do our sentiment analysis, parts of speech tagging, or other NLP task. That has a certain performance, and that certainly does work. But if you replace the tokenizer with a word to vec, so instead of assigning a one-hot vector to all the words, if we assign the v vectors that was obtained through the training of word to vec as the output of the tokenizers, and if we feed those v vectors into the RNNs, that significantly improves performance. Now, why would that be the case? Well, you see, if you use a one-hot tokenizer, then the word feline, the word cat, and the word truck, these are all just distinct words. They're mapped to just completely separate one-hot vectors. So the tokenization process does not provide any information as to which words are similar and which words are dissimilar. Whereas if you use word to vec, again, if you use word to vec, the words cat and feline will map to similar words, and the word truck will be mapped to a completely different vector. When you use this trained word level tokenizer, namely word to vec, as the input that the RNN starts out with already has this rich information in terms of the similarity and dissimilarity of certain words. Now, this word to vec idea was a groundbreaking idea, and it would go on to win the Test of Time Award in the 2023 NeurIPS conference. But it's still, I mean, there are improvements to be made, and there's a downside. So the downside of this idea is that, well, if you do this word level tokenizer, then it does not consider the context in which the word W is used in. So, you can have issues with polysemy. A word can mean multiple things. The word bank can mean different things depending on what kind of context it is used within. And if you use a word level tokenizer, the tokenizer cannot possibly consider the context in which the word is used. So these kind of ambiguities cannot be resolved. So we're going to fix this problem in the next model that we're going to talk about. But before we talk about the next model, let me quickly make a commentary about self-supervised learning. So in self-supervised learning, abbreviated as SSL, a model learns useful representations from unlabeled data by solving pretext tasks that automatically generate supervisory signals. The pretext task is not by itself useful. By itself, it's not useful, but it is related to downstream tasks of interest. The pre-trained model is subsequently trained on downstream tasks, usually with a smaller labeled data set. So it's instructive to look at this task from computer vision. So the pretext task that is being considered here is predicting the random rotation. So these images are scraped from the internet, and it is assumed that these images come in the correct orientation. Now, that's not always going to be the case. Some pictures on the internet will have the incorrect orientation, but most of them will have the correct orientation, so we'll go off of that. We take this image from the internet and we regard this as the correct ground truth correct orientation. Then we randomly rotate these images, so 90 degrees, 180 degrees, 270 degrees, and also 0 degrees. So there are 4 possible choices. And then a convolutional network is trained to predict the correct orientation. Again, this is a pretext task, and as far as I can tell, this task by itself is not very useful. But to be able to carry out this task with high accuracy, the model needs to eventually learn a lot of knowledge about what these objects are. And through this self-supervised learning, the model is able to use a lot of useful features. And then when you take this model and then fine-tune it or further train it on a small labeled data set, the classification performance, for example, if you consider classification as the downstream task, the classification performance is significantly improved compared to not doing this kind of self-supervised learning. The success of self-supervised learning has been observed in computer vision, but it is most dramatic in natural language processing. And word2vec was the first notable success case of self-supervised learning in NLP. So ELMo is the work that follows word2vec, and it produces an in-context tokenizer. So ELMo is the abbreviation of Embeddings from Language Models. And again, it's meant to produce an in-context tokenizer, tokenizing words to vectors while taking into account the neighboring context. ELMo uses a bidirectional LSTM structure. So here we have a sequence of one-hot vectors, and that's fed through a stacked RNN, a forward stacked RNN, and then a reverse stacked RNN. And these two forward and reverse directional processing is combined to produce the tokenized vectors. So ELMo is trained through self-supervised learning. For that, it needs training data and a pretext task. The training data for ELMo is just unlabeled text, just text written by human beings without any external labels. ELMo is then trained using the bidirectional language modeling loss. For the four-directional RNN, ELMo uses this next token prediction loss. So given the first L tokens, predict the subsequent token. And then for the reverse directional RNN, it performs a reverse directional language model. So given the later words, then predict the current word. So ELMo is trained with this bidirectional language modeling loss, and that makes it a non-causal language model. So a causal language model takes in as input the earlier tokens and predicts the next token. So a causal language model learns to predict the next token from left to right, the usual direction of our language. Whereas for ELMo, and soon we'll see with the model BERT as well, these are non-causal language models. Now you can say that half of ELMo is a causal language model, and that's certainly the case, but as a whole, it's not a causal language model. So the reason this distinction between causal and non-causal language models is worth pointing out is that ELMo and BERT certainly can understand language. So this language modeling loss, causal or not, is a useful pretext task in the self-supervised learning sense. So these do serve, despite being non-causal language models, they understand language. And ELMo and BERT can solve many NLP tasks, but it cannot generate text. In contrast, GPT is a causal language model, and because it is a causal language model, it can generate text. So if you want to have a model generating text, then you need the model to be a causal language model. So once this ELMo model is trained on this bidirectional language modeling loss as a pretext task, it is then fine-tuned for the downstream tasks. So given a prior NLP method, which can be very specialized, it can be very much tailored to the specific task, and if this prior NLP method takes in as input this X sequence, we replace the X of this prior NLP method with this X tilde, where this X tilde is the concatenation of this X sequence and also the hidden states of this LSTM RNN, the ELMo LSTM RNN. Then now the entire pipeline is trained. So this means training the trainable parameters of this prior NLP method and also the weights within this ELMo model. So this worked remarkably well. ELMo achieved a state-of-the-art performance on a wide range of NLP tasks, such as question answering, textual entailment, which is determining whether a hypothesis is true given a certain premise, semantic role labeling, which basically means answering who did what to whom, co-reference resolution, which involves clustering mentions in text that refer to the same underlying real-world entities, named entity extraction. So this involves finding four types of named entities: person, location, organization, miscellaneous in news articles, and sentiment analysis. I want to emphasize that this was highly, highly unusual at the time, because usually a good NLP paper would make advancements in one of these NLP tasks. But what ELMo showed is that through this general rubric, you can get improvements on all of these NLP tasks, not just one. And this is the kind of paper that shakes up an entire field. It tells people within NLP that the old way of doing things are now outdated. You have to do something like this to achieve the state-of-the-art performance. I'll mention that the idea of self-supervised learning through large-scale pre-training and then fine-tuning, this is not new. Indeed, Word2Vec is a predecessor of ELMo, and also the paper Dai and Le, 2015. This proposed an idea very similar to ELMo. But ELMo executed it very well, and it advanced the state-of-the-art substantially. ELMo made it clear that self-supervised pre-training is an indispensable paradigm in natural language processing. However, the LSTM RNN is not the best architecture. The left and right directional RNNs, it only process information unidirectionally. Yes, the two combined, you get a bidirectional RNN, but those two components individually, they process things unidirectionally. So since the components are all unidirectional processors, well, if the model needs to examine the entire sequence to make inference and kind of go back and forth between the different words, the RNNs are fundamentally computationally inefficient at doing that. Also, the overall approach of ELMo is still not universal. Each task requires an existing NLP method that we attach the ELMo to. So the ELMo really only serves to provide a better tokenization.